Okay, let's start. Uh, and Today Nikita Nikolaev will continue actually at his second talk about geometry and resurgence of WKB solutions of Schrödinger equations. So Nikita, please.
Okay, thank you very much. Okay, so last time I finished with this slide where I stated basically the main theorem of this paper that is in the title, and the theorem talks about WKB formal WKB solutions of a Schrödinger equation, and the claim is that these formal solutions are resurgent. And I gave this kind of quasi definition of what it means for a power series, formal power series, to be resurgent, um, which says that, well, it needs to kind of have two main ingredients. First of all, this power series needs to be Borel summable in almost every direction. And in those directions in which it is not summable, the reason it's not summable is perhaps because there is some kind of Stokes phenomenon happening. So for resurgence, what you need to be able to do is you need to be able to describe that Stokes phenomenon in an effective way, which in this business kind of means try to describe the Stokes jumps as Borel resummations of some other auxiliary related quantities. Right. So this is a quasi definition, and what I want to do for the rest of today is to take this definition apart, or rather figure out what the definition is actually supposed to be. In particular, in geometric terms. So the upshot is that this is really a problem in geometry. So the question needs to be asked in a geometric sense. Right, and so kind of developing the answer to the question of what should this definition be geometrically is kind of most of the work towards proving this theorem. Somehow, once you've set up the geometric content, then everything else is kind of straightforward. You just need to follow your nose. So this business is about what I would call infinite Riemann surfaces. So let me just rearrange my screen a little. Oops. Yeah, there we go. So it's about infinite Riemann surfaces. Okay, so the first definition is what I call a Riemann surface spread over C. So what that is a pair of a Riemann surface and a holomorphic function, global holomorphic function, non-constant. This is actually kind of a very classical notion. Like nowadays, when we say a Riemann surface, we don't think of this. We just think of one-dimensional holomorphic manifold. But actually, kind of originally, when Riemann was thinking about his surfaces and etc., this is the object that they were all considering. So when they would say a Riemann surface, this is what they would mean. And what we now understand by a Riemann surface is what they would sometimes call abstract Riemann surface, and they would really kind of shudder at the thought of considering such a thing. So anyway, it turns out that in this business, it's the more classical notion of a Riemann surface which is at play. So okay, so some kind of examples to keep in mind. So obviously branch covers, but also Riemann surfaces of multi-valued functions. So for instance, the second example here is I'm considering the Riemann surface of the logarithm. So the map, this non-constant function, is the inverse of the logarithm, which is the exponential. And then you can play with this and come up with weird, beautiful examples. So kind of the first thing I tried is plug in the sine function into the exponential. So that would be another example of a Riemann surface spread over C.
And also, And also, in particular, any open subset of C is a Riemann surface.
Oh yeah, yeah. Of course, yeah. So as long as you have a, as long as you are just taking a Riemann surface and a non-constant holomorphic map on it, this is going to be a Riemann surface spread over C. So the fact that
well, exclude the compact Riemann surfaces.
Close. Yeah, you could take a compact Riemann surface. Yeah, sorry. No, I mean compact Riemann surface with missing points.
Okay. Yes.
Yeah. So right. So anyway, so one thing to point out here is like this Riemann surface spread over C has. So it's the Riemann surface of the logarithm, and what we always think about when we think about the logarithm is the logarithmic singularity at the origin, and so that's going to be very important. So in the next slide, I'm going to try and kind of understand these things properly. But this is an excellent example to think about. So it's got this singular point at the origin in the image of the exponential, and we always think of it as a it's a singularity of the Riemann surface of the logarithm. But the funny thing is, of course, there's no actual singular point on this copy of C which corresponds to that logarithmic singularity, right? So as opposed to kind of algebraic singularities, which are ramification points, so are actual points on the Riemann surface, non-algebraic singularities are not like that. They're kind of missing. They're not just punctures or missing points. They're just there's something more complicated, and I will spend some time trying to describe how to think about them. So okay, but the main example of these Riemann surfaces spread over C comes from analytic continuation, and this is kind of completely relevant because the goal of proving the theorem that I stated is to take the formal Borel transform, the Borel transform, convergent Borel transform, and construct its global analytic continuation. So that's therefore you kind of very naturally end up in this realm. So let me recall one way to think about analytic continuation. And it's like this. So suppose I have a Riemann surface, which I'm calling Y, and every Riemann surface has an associated space called a Talé space, which is this kind of huge topological space. It's the disjoint union of all the Stokes at all the points of the Riemann surface. So here I drew a kind of a cartoon. So I have my Riemann surface Y, and above it I have this kind of huge, very, very large space whose fibers are spaces of germs, of holomorphic functions at that point. And suppose I pick a germ, a holomorphic germ at a point. So here's a point on my Riemann surface, and I pick a germ, phi hat. So it's going to be a point in this fiber, right? It's going to be a point in this space, and I'm actually going to think of it as a point in this topological space. And the way you define the Riemann surface of this germ, or in other words, the analytic continuation of this germ, you define it as the connected component of this huge space, a Talé space. It's the connected component which passes through this point that you've selected. So that's what I'm calling M. And it turns out that, so first of all, this connected component inherits a topology in which it is a Riemann surface. It's a holomorphic one-dimensional manifold. And this projection from the total space, pi, when you restrict it to M, that becomes a holomorphic map with respect to this holomorphic structure. So this becomes, this Riemann surface M comes with a map, a natural map to the original Riemann surface Y. And moreover, just because of the construction, this map in principle could have ramification points, etc. But this point, which I've selected, through which I've selected the connected component that I called M. This point is necessarily unramified. And so, well, okay, I skipped ahead here a bit. So yeah, this point, this distinguished point, which I'm now calling P, that's the point which represents the germ that I picked, P. That point is unramified, and so therefore my projection pi in the neighborhood of this point is actually a holomorphic isomorphism. And so I can use it to pull back germs from the neighborhood around Q to the neighborhood around P in M. I can just pull them back by this isomorphism. So in other words, what that allows me to do is I'm going to think of this holomorphic germ phi hat, which is a holomorphic germ on Y near, at the point Q. I am now using this canonical isomorphism. I'm going to naturally think of it as a holomorphic germ on this point P, on this distinguished point P on M. And so, right. And then the way you interpret this is that this germ phi hat is really just the germ of a holomorphic function phi, global holomorphic function phi on the Riemann surface M. You're just taking the germ of that at this distinguished point P. So that's one way to think about analytic continuation of holomorphic functions or of germs. And then, a very special case is if I take as my base Riemann surface just the complex plane, and then my distinguished point Q is just the origin in the complex plane, and I'm taking phi hat, which is now just a convergent power series. You literally just write down a convergent power series in T, the variable on Y. Then this Riemann surface M obtained through this construction comes with a map to C and a distinguished point. And so this is a Riemann surface spread over C, and on top of that it has a distinguished point which you could call the origin. Does this make sense?
So in the last example, convergent, do you mean convergent on the whole C or convergent in the neighborhood of?
Convergent in the neighborhood. So just a power series in T with finite radius of convergence. Okay, so one of the interesting things to think about and important things to think about when you're thinking about these Riemann surfaces spread over C is the singularities that they may have. So I've already indicated that when you're thinking about something like the Riemann surface of the logarithm, there's this kind of very interesting point, which is the logarithmic singularity, and it's a point in the codomain of this map pi, but not in the domain. But somehow the desire is to think of the preimage, so to speak, of this point as existing on the domain and call that a singularity. So how do you do this? So what I'm saying here is, these things, they come with a notion of singularities, and they always come in two kinds, algebraic and non-algebraic. So algebraic ones are very easy to describe. You just have a map, holomorphic map. This holomorphic map, its derivative may vanish at some point. Those are the ramification points. That's where the Riemann surface, as some kind of sheeted covering of the base, those are the points where it's ramified. And so those are the algebraic singularities. That's it, done. That's the definition. But if you are thinking about non-algebraic singularities, then you have to work a little bit. But here's one way to do it. So here I kind of gave an artistic impression of what the Riemann surface of a logarithm looks like. And this point in the base, which I've called psi, you can think that this is the origin, and this pi is the exponential map. So, so I want to, I want to understand the singularity on this Riemann surface corresponding to this singular value. So, okay, so I picked a point xi in the closure of the image. And here's what you can do. So if I take a small neighborhood of the singular value xi, and I look at the pre-image of that neighborhood, that gives me, so the thing that I've kind of colored green here, that gives me some open subset of M. And if I if I shrink U, then the number of connected components of this open set may jump, it may increase. But I'm always guaranteed that this number of connected components is countable, because pi is a holomorphic map. So so that means I can define a set of equivalence classes, or germs of connected components of the pre-image. So these are equivalences under inclusion. So in other words, two pre-images are equivalent if they are if they're contained in the same connected component of the pre-image. So this is this set of germs of connected components is something I'm calling F sub xi, and you could think of this as the fiber of pi above xi. It doesn't quite make sense to think of it as a fiber, because, for instance, if this were the exponential map, then the fiber of the exponential map of 0 is empty. There is nothing. But this is this set, this kind of germ set of equivalence classes of connected components, that would be non-empty. For the exponential map, in fact, that would be a point, or I should say a single element. So let me take one of those kind of single elements, Q. So it's an equivalence class of connected components. And what I'm going to do is I'm going to take all the open subsets belonging to this equivalence class, and I'm just going to take a total intersection. So this is some open subset of this is some subset of the Riemann surface M. And again, I'm going to use the fact that pi was a holomorphic map. That to me guarantees that there's only two possibilities for what this subset could be. So the subset could be non-empty, in which case it would be a single point, and in that case we would be looking at either a regular point on the Riemann surface or an algebraic singularity. And another possibility is that this set is empty. Well, again, there's two possibilities. It could be a removable singularity. So I would be able to actually, one of these U's would be like a punctured disk, and so I would be able to fill it in. But let me just assume that everything that could be filled in has already been filled in. So then in that eventuality, when it is not a removable singularity, then I'm going to think of this equivalence class Q as a non-algebraic singularity, or a transcendental singularity, and it's sitting above this singular value xi. And I can furthermore think of kind of representatives of this equivalence class Q as a neighborhood around this transcendental singularity Q. So again, you should just kind of keep, have this picture in mind, that there isn't an actual point in the pre-image of xi, but there is a sense in which, there's some neighborhood which represents closeness to points which get mapped very close to xi. Does this make sense? Any questions about this? Okay. Okay, so now one of the key definitions. So I'm going to look at Riemann surfaces which have singularities, both algebraic and non-algebraic, and I'm going to restrict my attention to a nice subclass, still huge subclass of Riemann surfaces, where the only singularities are isolated. Let me just kind of say, what does it mean isolated? So when you have actual points on the surface, it's very easy to say what it means to be isolated. It means the 2 points would have neighborhoods. You could take the neighborhoods to small enough such that they're disjoint. So when you have non-algebraic singularities, you don't have points, but you still have neighborhoods. So the idea is that if you have two, these math frac Q, so two equivalence classes, they have representatives which are disjoint. So that's what it means to be isolated. And such Riemann surfaces are called endless Riemann surfaces. So let me kind of make an important remark, which is that, so even if I have an endless Riemann surface, so sounds like a nice thing, I'm only considering isolated singularities. Actually, the set of singular values, so the kind of the image of all these singularities, that could be dense in the complex plane. And this is actually kind of a typical situation, certainly in Resurgence, that arises within the context of WKB, that you have the singularities in this complex plane C, which is traditionally called the Borel plane, and in that plane, those singular values are actually, they have accumulation points, and in a way that's a source of a lot of difficulty, because you're trying to kind of make or build some analytic continuation in this complex plane C, and your task is to continue it by avoiding all these singularities. And so if you just consider the totality of all the singular values that you have in this complex plane, you might have accumulation points. But this accumulation is kind of fake. It's just accumulating because really it's just a projection of many isolated singularities, but down an infinitely sheeted Riemann surface. And your analytic continuation should be really happening not in this complex plane C, but on that Riemann surface. And once you pass to that Riemann surface and try to do analytic continuation there, it's much more straightforward to do, because you basically have a discrete, possibly a discrete set that you need to avoid, which is makes much more sense as far as analytic continuation is concerned. Anyway, we'll get to that in more detail. Okay, so some examples. Again, I'm just repeating the examples that I gave before. You have branched covering maps, you have the Riemann surface of the logarithm. So this one would have a single transcendental singularity above 0. And then you could play with this. You could plug in the sign into the exponential, and this one would have infinitely many transcendental singularities above the singular value at 0. Let me give you quickly a non-example, the type of things that can go wrong. And so one fun way to create such non-examples is to kind of iterate logarithms. So here's what I'm doing. I'm creating a sequence of functions where I'm nesting logarithms. So the first one is I have it's the germ at 0. I'm thinking about germs at 0 in the t-plane. And I have a logarithm function that has a logarithmic branch point at t equals to 1, and then and then I plug that into phi 2. I get log of log, and then I just want to I pick some complex number Cn such that I arrange the logarithmic singularities or logarithmic branch points in the t-plane in the way that I would like. So and then you just take the limit of these functions. You get a germ, which I'm calling phi hat. And then the cool thing is that it's not so difficult actually but you can pick this sequence of complex numbers Cn such that you get a picture like this. So here I've arranged all the logarithmic singular values to lie on the real axis. Xi1 is, I guess, equal to 1 because I chose this one, and then you choose all the C's in such a way that there are singularities at a subset of the real axis, which is accumulating at some point, which I'm calling psi infinity, and it can be even cooler. Like you can arrange these constants in such a way that, you know, if I'm starting with this germ phi hat and I start analytically continuing it along the real axis and I encounter this first logarithmic singularity, then I have to make a choice. If I want to continue, if I want to proceed with the analytic continuation past this point, I have to circumvent it, and I could go on the left or on the right, and you can arrange these constants in such a way that, like the way I did it here, if you go on the left, then what will happen is that because of the nested logarithms, this point will suddenly be, you know, a zero of the logarithms, and so that would be a logarithmic branch point. But had I gone around on the right, then, you know, the kind of the argument inside one of my logarithms would be shifted by 2 pi I, and that would screw up the location of the zero. And so that would mean that if I avoided this singularity on the right and then looked straight ahead, I would not see this logarithmic branch point. I would just be able to do analytic continuation without any obstruction. And so here, actually, well, you know, you could do like this zigzag thing where, in order to see infinitely many singularities, you also always have to kind of go left, right, left, right, left, right, left, right, etc. So there's a lot of fun that you can have with these kind of constructions. Another one is, okay, so something similar, but now I've arranged these singular points not along a straight line, but along some kind of semicircle or something. And so, yeah, anyway, so all of these examples, they would break this endless Riemann surface definition. It's because I would be able to, you know, by doing the zigzag pattern, I would be able to reach a non-isolated singularity on my Riemann surface. So anyway, this transcendental singularity on the Riemann surface would be non-isolated. So that this would be an example of a non-endless Riemann surface. Okay, so right, so okay, so like I kind of talked about this example by, you know, continuing along a straight line, avoiding a singularity, seeing a singularity, not seeing a singularity, etc. So this is exactly the kind of game that you have to play in Resurgence, because Resurgence is about, well, it's about analytic continuation, and in particular about kind of trying to analytically continue my germ along a straight line to infinity, and if I fail, then try to whatever it is that's preventing me from doing it, try to avoid it, you know, on the left or on the right, and still proceed. And then you get these infinite paths, and then you want to take the Laplace transform along those infinite paths and hope for the best. And so okay, so now I'm going to kind of introduce a bunch of, well, more terminology related to the way you reach or not reach singularities. So far, any questions about any of what I've said? Okay. Okay, so let me fix, suppose I have an endless Riemann surface, m comma pi. P will be a regular point, so not a singularity. And then frac Q will be a singularity, transcendental or algebraic. And it's and this singularity is lying over a singular value psi. So okay, so one notion that's important is that if I'm sitting at a regular point P, and I have any kind of path passing through that point P, that defines for me a tangential ray, which is which just means a direction, direction in which I'm looking if I'm sitting at the point P. Invariantly, what that is you take the tangent space to your Riemann surface at this point P. That's a complex vector space, one-dimensional complex vector space, and that has an action, a natural action by rescaling by positive real numbers. So just picking out real rays in this one-dimensional complex plane. So if you take a quotient by this action, then you get something that I'm calling a tangential circle, S sub Pm, which you can make this construction for any Riemann surface, not necessarily one which is spread over C. And in this case, this would be a space that is isomorphic to a circle. But in our case, because we do have this map pi to the complex plane, and I'm assuming that P is a regular point, so that means pi is a local isomorphism near the point P to a neighborhood of its image. So that means its derivative, pi lower star, that induces an isomorphism on the tangent spaces. And so that isomorphism restricts to an isomorphism of these tangential circles. So one tangential circle on M at P, and one tangential circle at the image of P under pi of C. And this thing is canonically the standard circle, S1, because C comes with C is C, it has a coordinate. So in this case, when you're talking about Riemann surfaces spread over C, at every regular point, tangential rays can be literally thought of as, real phases of complex numbers. Okay, so that's one notion of tangential ray. Another thing that I can use this map pi to do is to have a notion of straight lines on my Riemann surface M, or what I'm calling geodesics. So if I'm looking at a path gamma on my Riemann surface, I'm going to call that a geodesic if its projection to the complex plane is just a straight line or a strain segment. So if I have a geodesic and its projection is a straight segment, that segment in the complex plane has a well-defined phase or well-defined inclination. And so you can use that notion to assign it to the geodesic. So if you have a geodesic on M, it has a phase which is a real number mod 2 pi z. Okay, then there's also a notion of an infinite path. So, in general, on a Riemann surface, non-compact Riemann surface, it may not, it's not obvious what it means to say I'm going to go off to infinity. But when you have a Riemann surface spread over C, that notion is very easy to define, and it's just you take a path on M and you project it down to the complex plane, and if that path goes off to infinity in the complex plane, then you call that an infinite path. And then another notion is about paths that hit singularities. Again, it's not an obvious thing to say because a non-algebraic singularity on M is not a point. It's not a point on M, so it doesn't really make sense that a path terminates at that point. But again, you can use pi to make sense of that, and the way you do it is you project that path down to the complex plane, and if that path limits to the singular value psi, then this path is a candidate for a path that terminates at a singular point. And so then to really say that it terminates at the singular point means that if I take any neighborhood which is a representative of this equivalence class, then that contains the tail of gamma. Does that make sense? Okay. Okay, and so this this language, it's useful. It's useful in the setting of resurgence because we're talking about reaching or avoiding singularities. And so in particular, I've already kind of used this word, visible singularity. So I started at a point P, and I tried to do analytic continuation along a straight line, and I hit a singularity of my Riemann surface, and I had to avoid it. And so what I really was doing there is I was traveling along a geodesic, which happened to terminate at a singular point. So I'm going to call a singularity Q, I'm going to say that it's visible from a given point P if I can reach it from P via a geodesic. So if there is a geodesic gamma that starts at P and terminates at Q. And then this kind of gives you an important notion of what should be a Stokes ray, or a singular direction, a direction in which the analytic continuation fails. So if I'm sitting at a point P, a regular point, and I start testing all the directions at P, all the tangential directions at P. And so what that means is I'm going to shoot out geodesics on my Riemann surface, and I'm going to record the directions in which the geodesic hit a singularity. And so I'm only going to see visible singularities this way. So I'm going to call all those directions Stokes rays. And so basically, here's a kind of a picture of what's happening in the complex plane downstairs, in the T plane. So I'm kind of this point, kind of the center of the complex plane here is the projection of P. And then what I'm doing is I'm shooting out geodesics, which means from the point of view of the T plane, I'm just shooting out straight rays, straight lines. And there are certain directions in which I have, in which this straight line in the T plane lifts to a geodesic that hits a singularity. And so that means if what I'm doing is trying to I have a germ at this point, and I'm trying to analytically continue it along all these straight lines, then there will be certain directions in which I cannot do this. And so what I'm going to do is I'm going to introduce a cut, in the sense of Riemann surfaces, a branch cut. And these are going to be all kind of radial cuts going off to infinity. And so you end up with pictures like this. This is a kind of a simple situation because I only kind of have finitely many directions in which I'm introducing a radial cut. And okay, so here's another way of thinking about the same picture, that I'm thinking of this circle. This is the tangential circle S sub PM, and that has special points which I'm calling Stokes rays. Those are the directions in which I have, in which geodesics with that phase terminate at some singular point. So yeah, as I said, this is a kind of a simple situation, but you could have kind of crazy examples, which do certainly occur, in the context of WKB, that you have accumulation behavior of these Stokes rays. So here I'm actually kind of picturing two different types of interesting accumulation behavior. So the top direction here, you see it's the dot is black. So that's what I'm suggesting here is that this direction, the kind of vertical direction, is not a Stokes direction, but it is an accumulation point of Stokes directions. And that is contrasted with what's happening at the bottom, where the straight down direction is itself a Stokes direction, and it's an accumulation point. So, all kinds of situations like this could happen. Does this make sense? Okay. Okay, so more about tangential directions, and in particular now I want to talk about what it means to avoid a singularity. So so I talked about this tangential circle at a regular point, and that was just you take the tangent space and you take the quotient by some natural action. So what about singularities? Can you say something about directionality or tangential directions at a singularity? So that's more difficult because, of course, again, the singularity Q is not a point, not necessarily a point on my Riemann surface. But what you can do, again, using the fact that you have this map pi to the complex plane, is you can take, you can consider geodesics, which are ending up, which are terminating at this singularity, and you can kind of devise an equivalence relation of paths, which is that if two paths have the same tail, or they coincide, their tail coincide after some point in time, then these paths belong to the same equivalence class. And so that gives you a notion of directionality. And so that I'm going to think of that as my as the analog of tangential directions, or the circle of tangential directions. And the cool thing about assuming that you have isolated singularities is that the covering map, the map pi, it still restricts to this set of equivalence classes to give you a map to the usual tangential circle on the base, which is an actual circle. But this time, it's not an isomorphism. It would be a covering. It would be a covering map, and so if the singularity is algebraic, it would be a finite, n to 1 covering map of circles. And if it's a transcendental singularity, then it would be universal covering. So this would be this thing would be isomorphic to the real line. Okay, but the because you have this map to the actual circle, and because this is now, it's a covering of a circle, you now get a completely natural notion of what it means to kind of turn around a singularity. So there's a perfectly well-defined notion of a exactly half revolution on the left or the right around a point. And so with this, you can define a notion of concatenation of two geodesics which terminate. Well, one of them terminates and the other one originates at a singularity. So I call this lateral concatenation. What happens is, so here's a kind of a cartoon image of what's happening. This is the picture of what's happening on the curve, but projected down to the complex plane. So I have these two.
I'm a bit confused. Kind of, you invented a lot of terminology of yourself, similarly to what Ekal did. All right, so you mentioned something about the dense set of singularities, how you can go from the left on to the right if there is a dense set. So if there is, maybe it's something due to the terminological difference, but
so this is why it's important. So I'm assuming that I have an endless Riemann surface, and so that means that the set of singularities on the Riemann surface it's isolated. The singularities are isolated. Their projections down to the complex plane, that may be dense, may have kind of bad properties. But
so that's a picture on the Riemann surface.
Yeah, exactly.
Okay.
So exactly, yeah. So that's why this assumption of isolated singularities is it's kind of key. It allows you to make all these all these arguments. So what I'm doing is, so because this singularity is isolated, I can kind of splice in a little half loop or a little loop that kind of originates in this direction and terminates in this direction. And so as concrete paths, so as real curves on the Riemann surface, they would obviously depend on how big this loop is. But as far as homotopy classes of these paths on the Riemann surface, they just depend on whether or not I'm avoiding it on the left or the right. And since we're going to be doing some kind of analytic continuation and integration, etc., everything ultimately depends just on homotopy classes. Right, so this is a well-defined notion for homotopy classes of paths on the Riemann surface or geodesics. And so kind of another way of saying essentially the same thing is that if I have a geodesic gamma, which is terminating at a singular point, at a singularity, then there's a canonical way to continue that geodesic in the same direction on the left or the right. So okay, so now you can then take kind of a bunch of geodesics and start laterally concatenating them, and you get what I'm calling a distorted geodesic. So it's something, you know, its projection down to the t-plane would look like this. It's just a straight ray with little loops spliced in, and well, so kind of part of the information of a distorted geodesic is this sequence of turns. Do I turn left or do I turn right? So that's, you just need to record a word on two letters, left, right. So you need to record the direction and a word. And so, right. So a singularity that I'm calling an observable singularity, not necessarily visible, but observable, is if you can reach it using a distorted geodesic. So not necessarily a geodesic, but a sequence of geodesics up to avoiding a finite number of points. And okay, so finally, the word that I've been building up to, which is an observable direction at a regular point, and that is just a pair of a tangential ray and a word, which I'm calling epsilon. So you just record how you're going to avoid the singularities. And then there's just a kind of a small coherence condition, which is that this word should stabilize. So I don't want to keep zigzagging it forever. Okay, so with that, finally, I can give a definition of what it means for a power series to be resurgent. And so I can state it like this. So a power series is resurgent is if, first of all, the Borel transform is a convergent holomorphic germ at the origin. And second, it admits endless analytic continuation, which really just means that the Riemann surface of this holomorphic germ is an endless Riemann surface. And then third property important for resurgence, which is some kind of boundedness condition at infinity, which ensures that I should be able to take the Laplace transform of this holomorphic function phi in some direction and obtain a result so that the Laplace transform would be well defined. And I should be able to do it in all directions which are non-singular, but also in all, along all infinite distorted geodesics, so that if I'm shooting out a ray in some direction and there's some singularities and I just avoid them, I get an infinite path and I take the Laplace transform along that infinite path, I should get that integral should converge.
So again, I'm a bit confused with terminology. Sorry. So your line C, where you can have a dense set of singularity, yeah? It's of course rectilinear. You can't speak about rays and take Laplace transform, but right. Since it's dense, it might be not kind of. It might be difficult to draw the okay, but you cannot speak about Laplace transform sitting on the Riemann surface. So then, which
you
one
can.
are
you can actually just because if you take one of these distorted geodesics, what that is really is a homotopy class of an infinite path in my Riemann surface. Right, it's avoiding all the singularities. And so that means in particular that it has like a tubular neighborhood, around it,
yeah,
which
okay.
is locally.
So its projection will be
Yeah.
your okay. Mm-hmm.
Yeah, yeah, exactly. Yeah, right. Okay, so I mean, thank you for the question, because it's kind of exactly leading me to the upshot, which is, what I want to kind of conclude is that to prove that something is resurgent, if you're given a quantity and you want to prove that it's resurgent, what that really means, I would argue, is to give a detailed description of this Riemann surface M, of its geometry. Like, what are the where are the singularities? What nature of these singularities? How, which directions do I need to avoid? How many terms do I need to take? All of that information, that's just geometric data. So, right. Okay, so let me give you one more definition of a kind of a class of resurgent power series, or a class of endless Riemann surfaces, which is particularly nice, and this is the situation that you encounter in exact-WKB analysis. So I'm not sure this is the best terminology for this, but anyway, this is what I call them in the paper. So you have an endless Riemann surface, and it's I'm going to say that it's of algebraic type if all the singularities of this endless Riemann surface are algebraic. So in other words, you have no transcendental singularities, you just have ramification points of pi. And then on top of that is built another type of endless Riemann surface, which is going to be relevant for us, which is the universal cover of such an algebraic type Riemann surface. So what I'm saying here is that this pair M pi is it's an endless Riemann surface of log algebraic type if there is some Riemann surface Y with a discrete subset, calling it gamma, such that if I take Y and remove this discrete subset, and I consider the universal cover of that, then M is that universal cover. And in addition, the map pi descends down this universal cover to Y, and so this Riemann surface, this endless Riemann surface Y pi is of algebraic type. So it's a very nice geometric setup. Basically, all you need to find is this Riemann surface of algebraic type, Y sub pi, and then take its universal cover, or the universal cover of its punctured version. And that's going to be the Riemann surface where you're going to be continuing your power series. And that's exactly what's happening in WKB. So, some not necessary remark. Okay, so the theorem that I stated at the end of last talk and at the beginning of today, I now want to kind of restate it in this much more detailed language that I've developed. So, suppose I have a marked curve, x, d, and I have a Schrödinger operator on this marked curve, which is satisfying the assumptions that I have in that theorem. So the two most important ones are that the associated quadratic differential phi has only simple zeros, and that the poles in the higher orders of the potential, they're kind of no worse than the poles of the leading order Q0, which is the quadratic differential. Then you could phrase the conclusion like this. You could say that the formal WKB solutions are resurgent of log algebraic type in all directions except the ones corresponding to divergent trajectories. And so specifically what that means is there exists a bunch of geometric data. So now let me explain or outline what that geometric data is. So first of all, there is
one question to the formulation. You consider local solutions because you mean the WKB, it has a parameter, this H bar, and the actual coordinate on your whatever curve. So you take a fixed point on the curve in the small neighborhood. Yeah, okay.
Right. Yeah. So I'm mixing two things here a little bit. So there's the WKB solution, and then there's that formal WKB differential. And WKB solution indeed requires a base point, and you're integrating something from that base point. But the WKB differential is this global thing on the spectral curve. And so here I'm slightly mixing the two notions, but I'm really maybe more thinking about this WKB differential because the WKB solution is written in terms of the differential. So, okay, yeah, good point. So maybe I should say the formal WKB differential is resurgent, and then the corollary is that the formal WKB solution is resurgent. Okay, so what that means is the following. So there is a two-dimensional holomorphic manifold, which I'm calling B and calling it the Borel total space. And that comes, that's a fibration by Riemann surfaces. So it comes with a surjective holomorphic submersion, S, which I'm calling the source map, fibering over the spectral curve punctured at the poles. And it also comes with a divisor. I'm saying horizontal divisor in the sense that it never aligns with the fibers of S. So it always intersects them transversely. And this is the divisor of Borel singularities. Okay, so that's one information. The second information is the covering space, or the kind of the fiber-wise, source fiber-wise universal covering. So it's another two-dimensional holomorphic manifold, which I'm calling B tilde, which comes with two surjective holomorphic submersions, one onto B punctured along the Borel singularities, and the other one onto the spectral curve away from poles and ramification points, which correspond to turning points. And then the third piece of data is another surjective holomorphic map onto the T-plane. T-plane is this Borel, Borel plane where we originally wanted to analytically continue the Borel transform. So what I'm saying is that there's really, the analytic continuation is not happening in the T-plane, but rather there's a map to the T-plane from a space where the analytic continuation is taking place. And so this map is what I'm calling the central charge. Okay, and so what are the properties of all this stuff? It's that, okay, so if I look at this Borel total space, and I look at the source fibers, so I pick a point P on the spectral curve, and I look at the fiber of the source map. I'm calling that the Borel surface at the point P. And if I take this central charge, Z, this holomorphic map, to the T-plane, and I restrict it to that fiber, that source fiber, so I get this map, Z sub P from BP to C, that gives me an endless Riemann surface. This pair of a Riemann surface and a holomorphic map on it, that's an endless Riemann surface. And in fact, it's of algebraic type. It's got singularities, only algebraic singularities, and they're all situated exactly along where this divisor gamma intersects the fiber. And this is a discrete subset. Then the other thing is that this holomorphic submersion, nu, the way I should think of it is as a source fiber-wise universal cover. So if I restrict it to a source fiber above P of B tilde, then that is nothing but the universal cover of the source fiber of B punctured along this discrete subset.
So may I ask you kind of to understand, because the geometry of Schrödinger equation is very simple, and there are too many quantors there exist. So you have your initial curve, and you have some, say, second order, whatever, rank 2 bundle with connection, blah, 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 which depends on H bar. So you have this spectral curve sigma, with delta, it's zeros, whatever, and ramification. Okay, good. Now, what is B?
So B, I was going to say this on the next slide, but B is the, let me just say it here. So B is the fundamental groupoid of the spectral curve punctured at the poles. So it actually, as a geometric space, it's very simple and very natural. And this.
Okay, so then your central charge.
Let me just display this entire slide.
It's a little bit unconventional. Let's see. Yeah, because your central charge is a kind of non-abelian. Typically, people take this pi1 modulo the commutator of pi1 with
Right.
itself, which is first homology.
Right.
And if for some reason you need non-commutative, well, it's not really important because it's you basically you restrict the Liouville form and you
right.
integrate.
Actually, you need to take this difference of Liouville form with its
with what?
So you take this. So iota is the involution on the spectral curve.
Yes.
Yeah.
Okay.
Yeah.
But morally, yeah. Okay, and you basically integrate this your central charge, and in fact, it's it's well defined on the homology. Yeah, this is clear. Now, gamma.
So gamma. Here's the definition of gamma. So these are paths on the spectral curve,
which end up in ramification points.
Yeah.
Okay. All right. Uh-huh.
Right.
Visible critical geodesics.
So right, these are paths along which the phase of the central charge is constant.
Yes.
Those are what I call geodesics. And if such a geodesic ends at a ramification point, that's a critical geodesic, and they correspond to what I call visible singularities. Those are the singularities that you will see by using geodesics.
Yeah, that's what Gayota-Morinetsky called BPS curves.
That's right. Yeah.
Yeah, they are stable objects in some category. All right.
Right.
Good. Yes. All right. Okay. Go on. Yeah.
Okay. Yeah. So, what was the last thing I mentioned? And So right. So the last bullet point here was just the fact that this Borel transform naturally extends to a global holomorphic function on this B tilde space, and this B tilde space is a bigger fundamental groupoid of a spectral curve punctured at more points, punctured at ramification as well. Right. Okay, so I'm almost out of time. Let me skip explaining more of the proof and instead give you.
Maybe you'll give an idea, because I see that you reduced the thing to the Riccati, to the nonlinear equation. Yeah.
Right.
And
okay.
how you handle it?
Yeah. Let me try to kind of explain. So basically, on the previous slide, I explained, or I introduced all these geometric gadgets, B tilde, Z, etc. And then the question is, why are those the relevant geometric objects? And the way you argue is this. So remember, I reduced the whole problem to understanding this power series F hat, which was in the WKB ansatz. And so that, when you phrase everything on a spectral curve, this F hat is the unique formal solution of a Riccati equation that looks like this. It has this form. And very importantly, the differential operator here, V, is this meromorphic vector field, which is dual to the Liouville form, or more accurately, to this double of the Liouville form. And so then you you want to take the Borel transform of this equation. So then you find that the Borel transform of f hat is a convergent power series in T, which is a holomorphic solution for small t of a differential equation that looks like this.
What star means?
Star is the is the convolution
okay.
in T. Yeah, and so when you look at this, basically the goal now is to construct global solutions of this differential equation. So that means in particular, there's this vector field v minus del t. That's the vector field you want to flow. You want to construct a global flow of this. And so then there's a number of groupoid theoretic observations. So first of all, this V has a canonical lift to the groupoid, which is it's called the left invariant vector field, or the source lift, and it's basically defined by this. It's S related to V, and it's tangent to the target foliation. So I'm calling this lift V tilde. So on the groupoid, on this geometric space B, there is a natural lift of the vector field V, which is somehow governing our differential equation. And then you make two crucial observations. You introduce this map, which I'm calling the anchor map, rho, which is you just combine the source map of the groupoid with the central charge. So that's a map from B to sigma cross the T-plane. This thing is two-dimensional, B is two-dimensional, this thing is two-dimensional. And the two key observations, well, okay, I'll say them in the opposite order, which is that this rho is kind of, for small t, it's actually an isomorphism. It's an isomorphism near the identity bisection away from gamma. And second, if you take this canonical lift of V to the groupoid and you push that forward using this anchor map, what you get is precisely this vector field, which you need to flow in order to solve this equation. And so then the idea is, the observation is that, okay, that means this equation really should be formulated on the groupoid, not on sigma cross T. So that's what you do. You transfer this equation to the groupoid using the anchor, and then that's where you're able to construct the global flow of this vector field. And so therefore you get a global solution just using some kind of standard fixed point argument. And that's the outline of the proof.
Yeah, you see, somehow it's I don't know, philosophically it's opposite to what people typically, physicists, and actually we with Maxim do, because you completely ignore the analysis of the geodesics on the spectral curve and how the number depends on the homology class, which physicists would call the growth of BPS invariants, which is, somehow you get it working entirely on the RAM side, which is strange. So then this central charge for you, it's not really the central charge, it's just in the difference of integrals of 2-1 forms. That's it. You do not really need to, okay. And, okay. Still something, no, I do not understand something. But maybe you'll finish and then we'll
right. May I just take like 1 minute and say a bonus thing which I've reserved here for the last slide. I'll just quickly go through it. So in recent weeks, I kind of applied the same groupoid theoretic point of view on resurgence to a Panlevet-1 equation, and I got something really, really beautiful. So this is work with 3 other people. So I'm looking at it's the deformed Panlevet-1 equation, which means there's an h-bar parameter like this. And so this equation is kind of very, very simple to solve in formal power series. You get, first of all, you get that there's an ambiguity, a square root ambiguity in T. So these formal power series really are properly defined on the double cover of the T-plane. Okay, and so, right, so then the theorem which we are preparing right now is that this formal solution is resurgent of log algebraic type. And the geometry behind it is very cool, because the space upon which the Borel transform is defined is an algebraic surface. It's a singular algebraic surface, which I'm calling B. Okay, let me skip to the second point. So this B, where I'm supposed to be defining my Borel transform with singularities, is actually a quotient of the Fermat quintic surface in C3. So this is your famous Fermat quintic surface, and there's an involution on it, which is basically just negation and, well, okay, here's the formula in the x, y, z coordinates. It's negation and swapping y and x. So if you take B, this Fermat quintic surface, and you quotient it by this involution, you get a singular surface which has a smooth, which has a locus, which I'm calling B star. It's a smooth algebraic surface, and it's basically on the universal cover of that, or fiber-wise universal cover of that algebraic surface, where the Borel transform of Q is defined as a global holomorphic function. And in fact, like this number 5 is recurring in Painlevé 1 everywhere, and this is no exception. So we got this quintic surface. It's fibering over the Z plane. Z plane is some fourth root cover of the T plane. So for some reason that's important. So over the Z plane, this quintic surface is fibering, and generic fibers are smooth quintic curves. And when you descend to the quotient, so when you're looking at B, when you're looking at B, so quintic surface mod the involution, on the fibers of that, those are the analogs of the Borel plane. Those have a central charge, Z, a map to the complex plane, and this is a 5-fold covering of the Z plane, ramified with exactly 5 distinct ramification points. So it's just five everywhere. Right, okay, so anyway, so this is the kind of statement you can prove using the techniques that I outlined. So, okay, I'm woefully over time, so I'll end here, and I'm looking forward to your questions.
Thank you very much. Now, last time you mentioned that you could prove in WKB setting that the set of singularities is exactly the values of the central charge. So how you can see this using these soft methods like existence of continuation of how you can allocate the set of singularities?
So that, I think that you can see from this slide, and it's basically, you could phrase it like this. So you would fix a point P on the spectral curve. That's the point, around which you're normalizing your WKB solution, etc. And that's the point from which you're going to be shooting out paths, and in particular geodesics. And so that means the relevant subset of Borel singularities is this subset that I'm calling gamma sub P. So that's just the intersection of this gamma with the Borel surface B sub P, which is participating because you've chosen the base point P. And so that subset is discrete. It's actually isomorphic to some copy of the power of the fundamental group. And now the Borel singular values, which is what you're asking about, would literally just be the image under the central charge of this subset in the T-plane. And those would be nothing. Like, let's see, if I pick a gamma inside gamma sub P, what is that? So gamma would be a path that starts at P and ends at some ramification point. So I would be, what is the value of Z on that gamma. It's just the integral of basically
Yeah.
the Liouville form. And in particular, if I pick a geodesic representative, that would be like integrating the Liouville form along one of the trajectories, one of its trajectories. And so you can see, therefore, that Z applied to gamma sub P is some subset, possibly with accumulation points in the T-plane, but all the values are what we know as, central charges is what this is what people call them.
I understand that you get all of them in this way.
Mm-hmm.
Okay, great. Now, more questions. So I don't want to kind of take all of them. So more questions, maybe comments. Because it's, of course, I think for people who hear this stuff, I mean, and Resurgence for the first time, they will be scared. I don't know. Yeah, this language of Gayota-Morinetsky, it's more kind of more intuitive, but it's difficult to prove
Right.
anything in that way.
Can I make a suggestion? So maybe it would be useful to explain just in a very simple way, like, one of the outcomes of this is that you identify a priori where the Borel transform is actually defined, and just emphasize that, just express it in terms of the original given data.
Yeah.
You mean
I suppose
after analytic continuation or what?
Yes. So in particular, what he's doing is he's identifying what is the Riemann surface precisely where the Borel transform has its analytic continuation completely, right? And the point is that you can describe it in terms of the initial data that defines the problem.
Right. So indeed. In this setting, I mean, it's very simple. If you take, if you're trying to, we're trying to analytically continue this function f, and it's a function of two variables: the variable on the spectral curve and the t variable with respect to which we want to construct an analytic continuation. So let me fix a point on the spectral curve. So that's a point P. So now I literally just have a power series in T, which I want to analytically continue. So the observation here is that the Riemann surface you should consider is the source fiber of the fundamental groupoid at of P above P. That's a fiber of this holomorphic manifold, and that's a Riemann surface. And that Riemann surface has a distinguished point, which is the constant path 1 sub P. So constant path at P. That's going to be my origin. That's the the origin in the T-plane lifts naturally to the origin 1 sub P in this Riemann surface. And furthermore, this Riemann surface has a distinguished discrete subset, which I'm calling gamma sub P. And this subset is discrete. And so therefore the Riemann surface to which I'm going to be analytically continuing this T power series is the universal cover, as I write it here, the universal cover of this punctured Riemann surface B sub P without gamma sub P.
Okay, but for people who are encountering this for the first time, this notation, okay, it might be helpful to explain that what this Riemann surface is, right? So let's follow what you said. So you start with sigma, the spectral curve. You remove delta, which is the
zero, so the quadratic differential.
Poles.
Poles.
Yeah, delta poles.
So you remove the poles, right? Then you take the universal cover of that.
Mm-hmm.
In that universal cover of the sigma minus the poles, you have a discrete set, gamma, which consists essentially of paths that go into the ramification locus. These are paths going from P into the zeros, these straight paths, right? And that discrete set in the universal cover, you have to remove it and take the universal cover of that.
Yep, that's right, yeah.
And that's your Riemann surf.
That is
that's the Riemann surf.
The Borel transform is defined, right?
Yeah.
So what I'm saying is, I'm giving you a piece of advice, which is you groupoidified everything in order to understand, but you need to degroupoidify it for the public.
Okay, yeah.
So that's a good advice. I am second. That, yeah. Yeah.
Okay.
More questions, comments, or advices to the speaker? Well, if there are none, well, thank you very much. Yeah, so it's indeed very interesting, I should say. Thank you,
Thank you.
Nikita. Well, and then this is it for today. Thanks for everyone.